We started this section by looking for solutions to the linear system of differential equations in the example y prime equals 5, -2, -1, 4 times y, where y is the vector function xy. On the direction field in the phase portrait, we noticed straight line solutions. We observed that on these straight lines, the position vector y points in the same direction as the direction vector y prime. That is, the straight line solutions y are scalar multiples of the tangent vector y prime. In other words, there are straight line solutions y1 and y2, so that yi prime is equal to lambda I times yi, for I equals 1 and 2. Moreover, each yi is a scalar multiple of some eigenvector vi. And as yi of t varies, so does that scalar multiple. So we have that these y's are equal to some function of t times the eigenvector v. We also saw that for two-dimensional systems like this one, if we can find two linearly independent solutions, then the general solution is given by y equals c1y1 plus c2y2. And since A has distinct eigenvalues, and thus the eigenvectors are linearly independent, if we find these two straight line solutions, then we can build the general solution. So all that remains is to find these straight line solutions. Now, for each of these yi, we know that it can be written as a scalar multiple f of t times the eigenvector v, and that y prime is equal to lambda y. We found the eigenvectors vi, v1, and v2, thus all we need to do is find fi to be able to find the straight line solution yi. To figure out how to do this, we want to think back to the beginning of the semester. Recall that for a first-order differential equation of the form y prime equals lambda y, we found that y equals e to the lambda t is a solution. From this insight, let's check if this is true for straight-line solutions yi of t to a linear system of differential equations that satisfies y prime equals lambda times y. That is, since straight-line solutions satisfy yi prime equals lambda I times yi for an eigenvector lambda, let's check if yi equal to e to the lambda it times vi is a solution to our linear system of differential equations y prime equals ay for this particular function yi. Notice here that our scalar multiple fi of t is e to the lambda it. At least that is our guess for fi, which is what we need to find. To check if this is a solution, we need to see if yi equal to e to the lambda it times vi satisfies the equation e to the lambda it times vi prime is equal to a times e to the it times vi. Let's compute each side and see if they are in fact equal. Let's first observe that e to the lambda it is a scalar, so we can change the order of multiplication here and do e to the lambda it times a vi. And since vi is an eigenvector with eigenvalue lambda I, we can rewrite a times vi as lambda times vi by the definition of an eigenvalue lambda and an eigenvector v. So this right-hand side is lambda I times e to the lambda it vi. On the left-hand side, notice that vi is constant, even though it's a vector. So when we take the derivative, we can pull it outside of the derivative. In other words, e to the lambda t times v prime is e to the lambda t prime times v. And e to the lambda it has the derivative lambda I times e to the lambda it. So on the left-hand side, we have lambda I times e to the lambda it times vi, which is the exact same as what we have on the right-hand side. So we've shown that if A has an eigenvalue lambda I with eigenvector vi, then yi of t equal to e to the lambda it times vi is a solution to the system of differential equations y prime equals a times y. So the main takeaway here is that we can find solutions to systems of differential equations by finding the eigenvalues and eigenvectors of the associated coefficient matrix A. Let's see how this works with the example that we had started. Returning to our example to find solutions to the linear system of differential equations y prime equals 5, -2, -1, 4 times y, we said that for two-dimensional systems like this one, if we can find two linearly independent solutions, then the general solution will be given by y equals c1 times y1 plus c2 times y2. But we also know that if A has eigenvalue lambda with eigenvector v, then y of t equal to e to the lambda tv is a solution to y prime equals ay. Since we found the two eigenvalues lambda 1 equals 3 and lambda 2 equals 6, with eigenvectors 1, 1 and -2, 1, we can conclude that y1 equal to e to the 3t times 1, 1 and y2 equal to e to the 6t times -2, 1 are solutions to our linear system. And since the eigenvalues are linearly independent, we can conclude that y of t equal to c1 e to the 3t times 1, 1 plus c2 times e to the 6t times -2, 1 is the general solution of our system. This example will give us a method moving forward to solve many more systems of differential equations.